Of all the careers in all the world that a person could aspire to, you ended up a professional space traveler. What was it that motivated you or inspired you to become an astronaut?
I grew up on the south side of Chicago in the 1960s, and I think there was a synchronicity of events that inspired me to be an astronaut. And of course, the backdrop is nothing less than Mercury, Gemini, and Apollo. That was a time in our nation where we aspired to great things and we achieved them. But it would have been irrelevant if that wasn't also the time that television entered, the family environment. And so as a young boy, I got to vicariously experience really the Gemini program is the first that I remember, and see the training that the astronauts went through, the rigors of the training, and then the space flights themselves, culminating in our landing on the moon in 1969. Even before the moon landing, though, I decided that I wanted to be an astronaut. It just seemed like a cool thing to do. I was also a budding young scientist, and I just loved finding out the way nature works. So those two things together really drove my young life. I used to do a lot of play acting of being an astronaut. I had a vacuum cleaner with a hose that became my liquid cooling unit walking out to the space launch pad. I turned those big ice cream tins by cutting a hole and putting cellophane over it, into a space helmet. And this is how I played with my friends. And it seemed very natural at the time because here was a nation starting the exploration of space. That continued through my time as a young adult and then a professional adult. And at the same time, we had the space shuttle program that was starting. And some of the people I had worked with became astronauts. Jeff Hoffman was a postdoc with me at MIT when I was an undergraduate. He became an astronaut in the first class of astronauts. So I saw a path. When I got my doctorate, I applied to be an astronaut, thinking, if I don't apply, I know the outcome. And I've just been incredibly fortunate to have been an astronaut, to have flown 4 missions and twice to the Hubble Space Telescope.
You mentioned that you're from the Chicago area. Tell me about Highland Park. Tell me about your hometown.
When I grew up on the south side of Chicago, it was kind of a rough neighborhood. And when my parents saw the prospect of my older sister going to middle school, high school, they decided that we would move to the north side of Chicago, Highland Park. And for me, that was a whole new ballgame. It went from exploring back alleys to exploring ravines and forests and the lakeshore of Chicago, which seemed semi-infinite, and opened my eyes to the outdoors. And I became much more of a nature freak and a tree hugger from the back alleys and sorting through garbage and things like that. It was a very exciting time of my life, and I felt that I could go on exploring the ravines forever, and that I was a Scott or an Amundsen, especially in winter, wading through deep snow with a backpack and a big heavy coat. And I would imagine that I was on another planet and that I was an astronaut. And that all became, part of my play, but I added those elements of, being outdoors and away from lots of people.
I guess you have a sense then that of how the places that you grew up really contributed to making you the person that you are.
Certainly true that the places and experience we have as children and young adults has a big impact on what we bring to bear on the space program. Growing up in Highland Park in high school, I had some very influential teachers. I had a math teacher who taught calculus that helped me learn to be in love with mathematics. I had a chemistry teacher who inspired us to work what was in the class and to go beyond. And then little things. When equipment would break in her laboratory, she'd say, well, John, do you think you could fix this? And so I'd take a spectrometer home with me, set it up in my bathroom, and play with it until it would work, keep it a few months longer, and then bring it back and say, okay, it works now. Learning to fix those kind of things is the same kind of work that I do on the Hubble Space Telescope. I've just refined it a little bit further.
Have you had a chance from orbit to pick out familiar spots in the Chicago area?
Absolutely. The most fun thing to do in space, and rewarding thing in many ways, is to look back at planet Earth. The Hubble Space Telescope missions are so busy, you rarely get a chance to do that. But after we deploy the telescope, we have some time to go and look at planet Earth and photograph the planet. And I usually go up with a list of places that I want to see. Now, Hubble was launched into a near equatorial orbit, 28.5 degrees, And so we don't get to see very far north, the places that I grew up. But certainly many other places that I love, we do get to see, not only in Houston and Florida, Houston where we live, as astronauts in Florida, where we launched from, but also places that I would love to go someday. The Kennedy Space Center is at the same latitude as the Himalayas, so we see that quite a lot. So I spend a lot of time looking down at the mountains of the Himalayas, imagining sometime when I'll have the time to go there and look.
You touched on this. Let me ask you to tell us a little bit more about your education and your professional background prior to becoming an astronaut.
I was always a young scientist trying to explore things, looking for fossils in rocks along the Chicago lakeshore, then going on to MIT as an undergraduate, studying math and physics. Even my first year at MIT, I was interested in space and cosmology. I wanted to know how the universe worked. I took a part-time job as a satellite operator for something called Small Astronomy Satellite 3, SAS-3. And so I would change the tapes and monitor strip chart recorders and make sure the spacecraft was operating, all for a couple bucks an hour, and just loved it. And it introduced me to the scientists who were working on the programs at MIT, and also scientists from other institutions who would come to visit. So I continued that work, also doing cosmology with a professor named Ken Brescher and Philip Morrison. And Philip Morrison was an incredible thinker and was one of the guys who developed with Drake, the Drake equation for the probability of life outside of our solar system. And at that time it was considered very improbable. We didn't know about any other planets. But we talked a lot about cosmology, and in fact I did work on the Hubble expansion of the universe with Ken Brescher, which is interesting to me now coming back full stream that I'm working on the Hubble Space Telescope, which also studies the expansion of the universe and has made some really startling discoveries that we never could have imagined back in the 70s. After MIT and spending 4 years doing astrophysics, I went on to spend a year at University of Tokyo, worked with a satellite doing X-ray astronomy that the Japanese had launched and helped launch a new satellite there, and then on to the University of Chicago, where I continued my education in astrophysics, cosmic ray physics, to get my doctorate, and then on to Caltech. It was at Caltech that I was interviewed to be an astronaut, and at that time couldn't imagine a better career. That I had spacecraft that I was working with, the Compton Observatory, Compton Gamma Ray Observatory, one of the great observatories along with Hubble. I had observatories like Palomar that I went to use big telescopes, the very large array of radio astronomy telescopes. I thought, this is fantastic. This is the golden era of astronomy, and I'm a part of it. I was studying neutron stars and black holes, which are incredibly interesting and exotic objects. I had wonderful students. I thought life couldn't be better. And then I got a call from Houston saying, John, we've reviewed your application and your interview. Would you like to come to Houston to be an astronaut? Well, I had to think about it for a millisecond or so, but the path was clear. And a friend of mine, Bruce Margon, who was formerly a deputy director on the Space Telescope project, said, John, it's an easy decision. You can always be an astronomer. This is your one chance to be an astronaut. And of course he was right, and I'd already made the decision. But it's been a glorious career, and I'm incredibly privileged to have been able to fly in space and to work on the Hubble Space Telescope.
Now we know that flying in space can be dangerous. So John, tell me what it is you think we get as a result of flying people in space that makes it worth the risk you're willing to take.
Space flight is inherently risky. I mean, you have to imagine sitting on 4.5 million pounds of explosive fuel and converting all of that chemical energy into kinetic energy of the space shuttle flying around the Earth at 17,500 miles an hour. One has to imagine it's risky to go out in a cloth spacesuit in a vacuum that's lethal to humans. So why do we take these risks? Why do I take these risks? I take these risks because I think that space exploration, science, the science that the Hubble Space Telescope does is incredibly important to humanity. We take risks every single day of our lives. Many of those risks we never think about. The risk you take driving from your home to your work on an expressway. Turns out that's a relatively risky thing to do. But do we think about that when we get in the car? No, because we've normalized that risk to that's what we have to do just to live on planet Earth. I think for the people of planet Earth, the kind of risk we're taking in the space program are worth the risk. And it's the risk that I accept as a risk taker.
When was the first time you ever heard of the Hubble Space Telescope?
As an astronomer, I was involved as a student first, and then a graduate student and a postdoc in a number of projects, all of them small. Looming in the background was the Great Observatory Program. And this was going to be a suite of telescopes in optical, infrared, X-ray, and gamma rays that NASA would launch over a period of years as flagship missions to unravel the mysteries of the universe. As part of that, a fellow named Charlie Pellerin made a Hubble coloring book. And I think it was Charlie who thought this would be a great way to distribute information about these great observatories. So I saw Hubble as the other observatories. It wasn't called Hubble then, it was, optical telescope, in this coloring book. As that Great Observatory Program progressed, the optical telescope, which would become the Hubble Space Telescope, was the first mission. And what I really saw was a mission sucking up all of NASA's resources in science, and as a looming threat on the horizon for this kind of small science that I was doing. But it was very clear that this was NASA's big flagship mission. And then, of course, after the launch of Hubble, it was in everybody's face, so to speak, because of the flawed mirror.
What has Hubble meant now to the science of astronomy and the work that it's done to this point?
The Hubble Space Telescope is more than remarkable. It has produced all of the science that we expected it would. The discovery that black holes really do exist and occupy the center of nearly every galaxy. Massive black holes, millions of times the mass of our sun. It's measured the age of the universe, 13.7 plus or minus 0.1 billion years old. Very accurate number. It's answered just so many of those fundamental questions that people have been asking about the cosmos since people were able to ask questions. From the science community perspective, Hubble is the specialist. It's kind of like, you go to your general practitioner and he says, well, I think there's something wrong with you, but we need a specialist to figure it out. Anytime we have a hard question in astronomy, that can be answered in optical astronomy, we turn to Hubble to go and answer that question. So Hubble is the perfect partner of the very large ground-based telescopes and the radio telescopes and the other space telescopes. But it's also that specialist where you need something that has to be answered that may be really difficult to do, then only Hubble can do it.
What has Hubble meant to the effort of space exploration?
In Star Trek, one of my favorite shows, we are trying to explore the unknown. And in science fiction, you have the advantage that you can travel faster than the speed of light and explore distant galaxies, do anything you want. In the world that we live in with real physics, that's not possible. And Hubble is our tool to go and explore the universe. Hubble is able to see back to within 700 million years so far of the start of the universe, to see the very first galaxies forming. It's been able to study what's between galaxies, to study stars and planets in our own galaxy. Keeping in mind that when Hubble was launched, we didn't know about any other planets in our own galaxy except our own solar system. All the way back to solar system exploration, where Hubble has been able to see giant impacts of comets, Shoemaker-Levy 9 on Jupiter and its effects, and study dust storms on Mars. Hubble allows us to do Mars exploration from Earth orbit. Even closer to home, Hubble has made the most dramatic and striking images of the moon since Apollo, and the first telescope to be able to do hyperspectral imaging, to do mineralogy in great detail, to study, what is the mineral content of the Aristarchus region of the moon. Pretty much everything.
And you've called yourself a Hubble hugger in the past. What has it meant to you as an astronomer to have participated in these repair missions to this instrument?
When I was assigned to STS-125, my first Hubble mission, it was like finding the Holy Grail. As an astronomer, this was a huge deal for me and the kind of thing that I had dreamed about since I was 6 years old. When I finally got there in December of 1999, I was on the end of the robotic arm and within about a meter of Hubble. And I really had one of those moments where I was kind of so thrilled that I just couldn't believe it, and found myself reaching out to touch Hubble. And I literally did that with my finger, to touch Hubble. to see if it was real. And of course it was. And then it was down to work, and for 8.5 hours we did nothing but work hard. But it was that, that one moment that really said, this is just incredible as an astronomer to be able to work on a telescope like this.
There are a lot of people involved in this effort now to get you and your crewmates ready to fly, and that's not going on just in Houston. Talk about some of the training and support that you've been receiving from the people behind Hubble at the Goddard Space Flight Center and the Space Telescope Science Institute.
The Hubble Space Telescope doesn't make discoveries. People make discoveries. And the Hubble is the ultimate team machine. Just to be able to go service the Hubble Space Telescope, we need 7 astronauts and a space shuttle. And that space shuttle needs tens of thousands of people, all to do their job right before it can successfully get to Hubble. From the science team, there are thousands of astronomers who work to look at the science from Hubble and then produce those discoveries. The people who train us from the Goddard Space Flight Center, who support the science teams, are another group of a couple hundred of the most dedicated scientists and engineers, certainly that this space agency has seen probably in its history, where they work long hours, tirelessly, and they're selected to be the best and brightest. It's an amazing group of people. When you look at that whole ensemble of the team, I think it's something that this country should be very proud of.
It's no surprise, I guess, that the people who are working on this mission love the Hubble Space Telescope, but Hubble's become something of an icon outside of the science community. Got any feeling about why it seems to have touched so many people in that way?
Astronomy is an ancient science, and for whatever reason, people want to know the answers to some fundamental questions. How did we get here? How did the universe start? I mean, that's another way of asking, how did we get here? How was the stuff that we're made out of produced? Where are we going? What's the ultimate fate of the universe? Hubble has been a tool, more than any other telescope, that has made accessible to the public answers to those questions. Not only with the scientific data and the answers, numbers like 13.7 billion years old for the age of the universe, but also unbelievable pictures of what the universe looks like. I think the public had not a terrific view into what the universe is like until we had the Hubble Space Telescope. As a result, people associate those images with the beauty of the universe, the numbers and the answers we get about the universe beginning with a Big Bang, and the age, and chemical elements being built in stars, turning into planets, solar systems. All of that information mixed in with these beautiful pictures has allowed Hubble to actually be an icon for science and an icon for the answer to fundamental questions.
The pictures. What's your favorite Hubble picture?
When I'm asked what's my favorite Hubble picture, boy, that's a tough question. Hubble has produced so many fantastic images, but there are 2 pictures in particular that I have to consider my favorites for a very fundamental reason. And I'll tell you what the pictures are first, and then the reason. The first is a picture of the Eskimo Nebula that was taken early in the year 2000. And this is a picture of what our sun may look like someday. It's a normal star, something like our sun, that at the end of its life has started to produce these little explosions that the star that continues to burn lights up and creates something we call a planetary nebula. The other picture is called the Tadpole, and it was taken by the Advanced Camera for Surveys in 2002. And it's a picture of actually 2 galaxies that are interacting, and it has a long tail, and it looks kind of like a tadpole. And it's a galactic collision. Fascinating from an astrophysics point of view. But even more so, in the background are about 6,000 galaxies, which opened my eyes to the fact that from now on, once we installed the Advanced Camera for Surveys, every picture we take would have this depth that we had never imagined before. Now, why are these my 2 favorite pictures? Because after 1999, the Eskimo Nebula was one of the first pictures the telescope took after we serviced it on STS-103, and the Tadpole was one of the first pictures that the telescope took after STS-109, proving that we hadn't broken the telescope and that it was still working.
You're a mission specialist and lead spacewalker on this Hubble Space Telescope servicing mission. John, summarize the goals of the mission and tell me what your main responsibilities are going to be.
We have 3 main goals on this mission to the Hubble Space Telescope for STS-125. The first is to put new scientific instruments in. The amazing thing about the Hubble Space Telescope is that it has a capability to be serviced by humans and represents the best marriage between human spaceflight and robotic science spacecraft. And that marriage allows us to upgrade the telescope to give it new capability. If you look at the original Hubble Space Telescope that was launched in 1990, no one at that time could have imagined the capabilities in the detectors, the cameras that we put on Hubble, and the scientific instruments that we have available now. And that's what we're going to put up with the new Wide Field Camera 3, which is an incredible camera that's really going to open up sort of the doors of Hubble for new discoveries, and the Cosmic Origin Spectrograph, which is going to be the best spectrograph, dividing light into all its component colors to allow you to do real physics. Those two instruments are our primary goals to make Hubble a much better telescope. Now, in order to allow those instruments to operate, we also have to do some regular servicing, just like your car, things that you know are going to wear out that you have to upgrade. And the principal components for that on this flight are going to be putting in new rate sensor units, which are the gyroscopes that allow Hubble to point so finely, new batteries, and a new fine guidance sensor. These are the tools that Hubble uses to operate to allow the scientific instruments to get their interesting results. And then there's always the things that just break on the telescope, and we'll go and fix a few of those things.
You know, after the loss of Columbia, this final Hubble servicing mission was canceled. It was decided that it was too risky. But that decision was reversed, and here you are. What was your feeling at the time about the decision not to fly to Hubble, and then your feeling about that decision being changed?
To understand why the decision was made not to go back to the Hubble Space Telescope with the space shuttle because of the perceived risk, you have to put your brain into the psychology at the time. And at the time, you know, we were all still reeling from the tragic loss of the crew of Columbia on STS-125. We had just received the Columbia Accident Investigation Board report, which had a whole list of things that were recommendations to NASA that we should do or had to do before we could resume flights of the space shuttle, if ever. And at the time, that if ever for any missions was still on the table. And so Administrator Sean O'Keefe made the decision not to fly back to the Hubble Space Telescope. Well, as a certified Hubble hugger, that hit me like a 2x4 in the head. I just couldn't believe that we would prematurely make that decision. On the other hand, at that time, I was the chief scientist of NASA, working for the administrator, working as part of the leadership team. And I had decided, if I was going to accept that position, that I would be a team player and work towards the goals of the agency, and the administrator sets those goals of the agency. As a result, my role was to ask the simple question, well, if we can't service Hubble by the space shuttle, how can we service Hubble? And so I helped to initiate a program for robotic servicing, because my interest was that Hubble could continue to do science and that we could continue to upgrade it by some means, and perhaps in the equation of doing robotic servicing, we might even be able to advance exploration by teaching the agency and allowing us to learn new tools of the trade for doing things in spaceflight. The crux of your question, though, is how did I feel as a risk taker versus a risk manager? And risk managers make decisions about whether you undertake a certain risk or not. Risk takers decide whether, you know, we're going to accept that risk and go service the Hubble Space Telescope.
Did the two sides of you have different feelings?
And my position that I spoke, I think, clearly about at the time, standing next to Mr. O'Keefe, is I would not have made the same decision because I'm inherently a risk taker. And it was his role to make the decision on whether, on our behalf, on the agency's behalf, we would take that risk. I'm just thrilled to be here now, and the real kudos have to go to the amazing Space Shuttle team, the contractors, all the people who have worked through those Columbia Accident Investigation Board recommendations to the point that we never thought we would be in the Space Shuttle program, that we're now confident that we can launch to the Hubble and return safely. It's been a tremendous effort, fixing the foam on the tank to the point we're comfortable launching, fixing all the other problems we identified subsequent to the loss of Columbia to make this a much safer system.
As a result of those recommendations, all shuttle flights now do a thorough inspection of the vehicle using the orbiter boom sensor system. Tell me a little bit how that's accomplished and what it is you're looking for when you do those surveys. When
the Space Shuttle launches, it's not a gentle event. the main engine's light, the vehicle starts to shake. Then at T0, the solid rocket motor's light, and you're in for a rough ride. And it's not just us in the cabin that are getting bounced around, but it's the whole system. There's also a lot of interesting physics going on with supersonic shocks and heating. As a result, we're still seeing foam loss, and that's just inherent to the system that we designed. There's also ice coming down. We've got cryogenic hydrogen and cryogenic oxygen, liquid hydrogen and liquid oxygen, and they cause moisture in the air to freeze. We're never going to eliminate those problems with the space shuttle. So as we go up on our ascent to orbit, there are still bits of foam and ice that are going to come off and are going to hit the shuttle. When we get to orbit, we want to spend a lot of time looking very carefully at the bottom of the orbiter and at the wing leading edges. And we do that with cameras and laser systems to look for any dings, cracks, any indication that one of those pieces of debris may have caused a problem that would prevent us from landing safely. Well, what could we do if we find one of those problems? Well, we can go out by spacewalks and hopefully fix it. As well, for this Hubble mission, we're going to have another orbiter standing by on the pad. So if we suffer irreparable damage, rather than being able to hang out on space station, which we can't do, we'll be able to launch another shuttle as a rescue flight.
There have been some tests of repair techniques done since return to flight. What could you fix? What damage could be repaired on orbit?
One of the things that the Columbia Accident Investigation Board said is, if you're going to launch space shuttles again, you got to have a repair option. But I think there was a lot of skepticism that we'd be able to repair anything, that was so significant that it would prevent the space shuttle from entering. NASA engineers never discount their creativity and ingenuity. They've come up with a variety of repair techniques, from special covers that we can put over the leading edges of the wings with little molly bolts that pull from behind, kind of like repairing something in the wall of your house that got damaged, but with that amazing heat shield capability on them, to just painting with a special coating that will allow damaged tiles to re-enter safely. So we can accommodate damage due to relatively small foam hits on the leading edges. We can accommodate damage to micrometeoroid debris, a little bullet from space that might penetrate our heat protection, from foam hitting tiles that causes a divot to come out of the bottom. Quite a wide variety of stuff. And then what we've seen in real flights with our white insulation blankets that maybe peel up from just the air rushing by. We found that we can push those in and sew them up with titanium thread.
All the work to get Hubble back running at full speed, of course, is contingent on you and your crewmates getting there and grabbing it out of the sky and putting it in the payload bay. Tell me about what part you play in those operations, and describe how you go about getting Hubble on that work platform in the payload bay.
So the first challenge is, of course, getting to orbit. And the amazing space shuttle system takes care of most of that. Once we get to orbit, we have to chase down and grab the Hubble Space Telescope. And we do that through a series of orbital mechanics maneuvers till we get right underneath the Hubble. And then Megan MacArthur, running the shuttle robotic arm, will reach out and grab the Hubble and put it down onto a platform in the payload bay where we'll latch it down, and that becomes our work platform then to do the spacewalks over a subsequent 5 spacewalks. We have doors on the Hubble that we open up and can take objects in and out, running bolts, and we can talk more about that in EVAs.
Once you get the telescope in the payload bay, there's a couple of hours initially set aside for a survey. What is it we're looking for at that point?
The Hubble has been in orbit for 18 years. It's a remarkable period of time for any spacecraft to be operating at the level Hubble has, and in an environment that's pretty nasty. At 600 kilometers where Hubble lives, there's little micrometeoroids that pepper the surface. In fact, on one of the high-gain antennas, there's a hole about this big where something went through, probably very high velocity. There's atomic oxygen, which eats away at the surface. There's solar ultraviolet radiation, which, just like us, Hubble gets a sunburn. And then there's thermal cycles. Once every orbit, about 95 minutes, Hubble gets heated by the sun and then cooled by radiation to space over and over again on all these cycles. And that takes its toll on the telescope. So on the day that we grab the Hubble, we're going to spend a lot of time with telephoto lenses and with the robotic arm and a camera surveying the outside of the Hubble to capture what its condition is before we start doing the spacewalks. And that has two functions, one of which is just historical data on what the outside of the telescope looks like, and the other to look for anything that's happened to Hubble since the last visit that might cause us problems during servicing, a piece of multi-layer insulation that might have peeled up around something that we don't want to disturb, or maybe we have to put it back down, things like that.
Now, you've been preparing for a set of spacewalks to the Hubble on this mission that are at least similar to what you did on your last mission. How has your experience of having done this before, twice before, helped you get ready to do it again?
I feel like I've been training to service the Hubble Space Telescope my whole life, working on scientific instruments in college and graduate school, and then as a professional researcher. All of those tools and techniques that I learned, I applied to my first Hubble Space Telescope servicing mission, STS-103. I then had the privilege of going back for STS-109. So I feel like I have a good tool set of lessons learned and also just raw experiences that I've been able to then apply in the development of the tasks that we're doing on STS-125 and also teaching the new spacewalkers those things that I've learned from those missions. Between Mike Massimino and myself, we've serviced many parts of the telescope, and I think we're able to bring to bear a lot of leverage that'll help us be successful on this one.
Getting ready for this one, does it feel different than the previous trips?
Getting ready for this mission is a little bit different from the previous trips in that it's been longer since we last flew, 6 years now, but also because of the loss of Columbia. It's just a different experience. There's a lot more that we have to do on this mission with the inspections and the surveys, learning the repair, so it's just got more content in addition to the Hubble Space Telescope repairs and servicing that we're going to do.
Help me set the scene for what's going to happen here. The timeline calls for 5 spacewalks to be conducted over 5 days. What's the cast of characters? How do you guys divide up the responsibilities of all the things that have to be done?
We're doing 5 spacewalks. We're doing a marathon at a sprint's pace, and then we come home. And that starts with Megan MacArthur grabbing the telescope. Then on the first EVA, Drew Feustel and myself will go out, do the first spacewalk. That will install the wide field camera and the batteries and set the stage for the second spacewalk, where we'll do the gyros and the second set of batteries. After that, the telescope will have been made perhaps 20 times better already. When we go into the third day, Drew Feustel and myself go back out. And on that day, we're going to install the cosmic origin spectrograph and then try the first of these oddball tasks for Hubble that have never been done before. And I'll talk a little bit more about that. But that's the Advanced Camera for Surveys repair. On the fourth EVA, Mike Massimino and Mike Good will go back out, and they'll try the second of the oddball repairs, the Space Telescope Imaging Spectrograph repair. Again, these 2 repairs, Advanced Camera for Survey and STS, involve techniques that we've never done before in Hubble. And then finally, Drew Feustel and myself will close with a fine guidance sensor swap. And if we haven't finished the Advanced Camera for Surveys, we'll do it at the end of that EVA. We come in, the next day we'll deploy the telescope. Again, Meg MacArthur will reach out with the arm and let go. Scott Altman, our commander, will fly away, and the whole team supports all of these activities.
While you're outside, who does what inside?
The Hubble EVAs are complex and in some cases very difficult. And while we're outside in our big white spacesuits, we don't have the repair manual. So the crucial element in all spacewalks, but in particular on these Hubble Space Telescope missions, is that the IV crew member, the inside man, has the procedures and is the spacewalk choreographer. He's actually the one running the show and keeping us on the timeline, monitoring our suit functions, but also helping to make sure we do the right thing at the right time, each step by step. Any mission, and the Hubble in particular, is built up of doing an individual step correctly and then stacking them all in the correct order.
So who will play the role of this inside wizard?
We're each going to take turns, depending upon which day it is, being the spacewalk choreographer, spacewalk master. On the first day, Mike Massimino, with his experience from the previous mission, is going to be the opener to get us out of the airlock and for the wide field camera 3 repair. And then after that, we kind of switch back and forth on tasks to give each person a break throughout the rest of the mission.
So we've got 5 spacewalks that 4 of you are going to conduct. I'd like to learn what it is that, what the tasks you're going to do or how they're going to change Hubble. The top priority components that you're installing, you mentioned before, the new rate sensor units. What are they and what will they do?
The rate sensor units on the Hubble Space Telescope are one of the tools that the Hubble uses for its fine pointing. There are a number of reasons why Hubble is the best telescope in the world, or in this case off the world, one of which is it can point very, very stably, which means it can look in one spot of the sky for a long, long time. The other reasons are it's above the atmosphere, and so the atmosphere doesn't flicker, so it can get very fine images. And some of the light that comes from stars, planets, galaxies, doesn't even get through the atmosphere, so you have to be above the atmosphere. Hubble can point so accurately that if you were on top of the Empire State Building and you aimed a laser pointer at the Washington Monument, it could hold that laser pointer on a dime that somebody's holding on the Washington Monument. The way that it does that is through the use of these rate sensor units and some other components in its pointing control system. However, these gyros are just like any other mechanical gyros. They have a little rotor that spins, and over time those rotors wear out. The bearings wear out, other things can happen. So Hubble carries 6 little gyroscopes in 3 rate sensor units so that it can operate for a long time. Well, right now we're down to 3 of those little gyroscopes. It needs 2 to do science, and in 1999 we did our quick deploy mission because it had got down to the minimum number and couldn't do science anymore. So we're going to put a brand new set of 3 rate sensor units, so we'll have a full complement of 6 gyros on the telescope.
The next priority is the Wide Field Camera 3. Is that a big improvement over Wide Field 2?
The Wide Field 2 camera that was put in on the first servicing mission was put in for a couple of reasons, but the primary one was built into Wide Field Camera 2 was a little mirror that corrected the aberrated optics of Hubble, which was the big catastrophe when Hubble was launched. The technology that went into that camera was state-of-the-art at the time, but we're talking about 1990. Imagine what kind of digital camera you could buy in 1990. Well, you couldn't. They weren't on the market yet. Well, nowadays, of course, you can go out and buy phenomenal cameras, and the astronomy community can create even better cameras for astronomical research with very large sensors, with lots and lots of pixels, and that can see over a wider range of frequencies. So Wide Field Camera 3 also will contain that little mirror that corrects the optics, but it will also have an infrared camera that can see light that's much longer than our eyes can see, but is very important for astronomy, and visible and ultraviolet in another channel. So it has this infrared and this ultraviolet visible channel, all of which have better detectors, more sensitive, that can see much, much dimmer things than the previous cameras could see on any part of the telescope. Plus, it's a wide field telescope, as its name sounds, so it can see large extended objects. What kind of things are we talking about? Well, we're looking at everything from planets in our solar system, the moon even, out to perhaps the most distant galaxy that will ever have been seen because of this increased sensitivity and because of the infrared part of the Wide Field Camera 3. As you look farther and farther back in time, because of the expansion of the universe, objects get redder and redder. They get red-shifted. And so this new Wide Field 3 camera promises, with the sensitivity of Hubble's optical system and the detector, to see further back in time, closer to the Big Bang than we've ever been able to see before.
Another of these new instruments that wasn't available before, the Cosmic Origins spectrograph, which is being installed in the spot occupied by another component called COSTAR. What will Hubble be able to see with the Cosmic Origins spectrograph installed?
The Cosmic Origins spectrograph is a physics machine, whereas the Wide Field camera is taking images which contain a lot of physics and a lot of information. The spectrograph takes the light that's coming from an object and breaks it up into tiny little bins by frequency and allows us to see spectral lines that are caused by oscillations of electrons and atoms, transitions between states, and from that you can tell the temperature, the density, all kinds of important details of what's going on, say, in a stellar atmosphere or in the gas between stars. And in particular, the cosmic origin spectrograph is going to investigate the space between stars in our own galaxy, interstellar medium, and even more important, the space between galaxies in the universe. When the universe was made, just like when you build a house, there was a lot of stuff left over. And the shape of that stuff is a critical factor in determining what the nature of the universe is, and in particular, subjects like dark matter. Because normal matter, the stuff we're made out of, hydrogen gas, helium gas, all the atomic elements, will clump around this dark matter that has the same effect of gravity as regular matter, but doesn't interact the way normal matter does with light, so we can't see it. And it turns out the structure of the universe is dominated by this dark matter. The cosmic origin spectrograph will be able to look through the universe and, using this physics tool, help us understand what the universe is made of and how it was formed.
I mentioned it's going in a spot that's currently occupied, the Corrective Optics Space Telescope Axial Replacement, or COSTAR. Why is that being retired now?
The COSTAR was the savior instrument for Hubble for all of the instruments that are the axial instruments. There are two different types of instruments on Hubble. There are radial instruments where the light comes out radially, and there's axial instruments where it goes down the long axis. And the radial ones are good for very wide field imaging, and that's why the wide field camera goes there. And the axial instruments are very good for sort of the zoom view. An example of that is the advanced camera for surveys. When the telescope was discovered that the mirror was a little too flat and was aberrated, the pictures were aberrated, just means they were messed up. Some smart person figured out that, well, if we could put essentially a contact lens in the view, we could correct that. Well, at the bottom of the telescope, there are 4 axial instruments. So they decided they would take an instrument out on the first servicing mission, put in COSTAR, and COSTAR would reach up into the optical path and put out these contact lenses so the other instruments could see straight. That worked, and the telescope started producing all these great discoveries. But on each subsequent servicing mission, when we put new instruments in, we were able to incorporate that contact lens into the new instrument. So now that we have the STS instrument, the NICMOS instrument, and the ACS, Advanced Camera for Surveys instrument, each of those has its own corrective optics. So COSTAR just isn't needed anymore. So the opportunity on STS-125 we have is to take COSTAR out, put the cosmic origin spectrograph in, which also has its own corrective optics, and for the first time in Hubble's history, we'll have 4 scientific instruments that all correct for the aberrated optics and will be up and operating, assuming we can fix ACS and STS.
Well, you're also bringing up 2 battery modules. Tell me about those. How long are they going to be able to last in this environment?
Hubble operates with nickel hydrogen batteries. And the batteries that are up there now have been in operation for 18 years, but they were produced many years before that. Originally, Hubble was going to be launched in 1985. So these batteries every single day are setting records for how long spacecraft batteries can operate, keeping in mind that they charge and discharge once in orbit, and have been doing that for 24 hours, 365 days a year for 18 years. So these are phenomenal batteries. However, they're down to half their capacity. And we want Hubble to be able to have a long and happy scientific lifetime on orbit, so we're replacing them with new batteries. These batteries were also manufactured a number of years ago, but they've been kept in cold storage. So once we put the 2 new batteries on, Hubble should have every capability of lasting another decade at least without the batteries being the problem.
You're also bringing up a refurbished fine guidance sensor to install. How does a fine guidance sensor work with the other components to get Hubble pointed where the scientists want it to look?
There are lots of ways that the pointing system on Hubble acquires targets, locks in on those targets, and then allows the science to be produced. It has some eyeballs on the outside of the telescope, which are the fixed head star trackers, and they kind of give Hubble that Snoopy look. And they acquire, the general orientation of the telescope, just as, the ancient mariners did by looking up at the sky as they were crossing the ocean. Once you get into the vicinity of where you want to look, the fixed head star tracker's job is done, and the fine guidance sensors take over. And what they do is they steal a little bit of light from the primary mirror. The light goes up from the primary mirror to the secondary and through a hole in the middle of the primary mirror. And the fixed-head star, the fine guidance sensors take that light, look at stars, identify them, lock onto them, and that's how the telescope points in the right place in the sky. And then the rate sensor units take care of, all the little oscillations and disturbances. All these parts work together.
We've been talking about new things you're going to put in, replacements, but you've also alluded to the task of repairing the Space Telescope Imaging Spectrometer, the STS. Tell me about what it sees and what's wrong with it and how you're going to try to repair it.
The Space Telescope Imaging Spectrograph is another instrument which is an astrophysics instrument. It takes light from a star or a planet or a galaxy and passes it through a slit. And once it goes through that slit, it then goes through the equivalent of prisms to break the light up into the component colors so that you can understand the physics of what's going on. It was the STS instrument that was crucial, for instance, in unraveling the dynamics at the center of a nearby galaxy to determine that there was a million solar mass black hole at the center and that they really existed. And it does this because when the light goes through the slit, not only does it look at the spectrum, but it looks at the spectrum across the range of that slit, so it can do both imaging and spectroscopy at the same time. It's a unique instrument in the history of physics, in the history of astronomy, to have in space, and it's uniquely suited to do certain kinds of work. Unfortunately, it's not working right now. It suffered a loss of a power supply that provides voltage to the scientific instrument. Unfortunately, the brilliant people who designed the telescope said, let's make sure every instrument has two power supplies. So if one fails, you switch to the other, and that's what we did. And then the second power supply failed. One of those power supplies is in the front of the instrument. And so we're able to take a cover plate off, pull a circuit board out, put a new circuit board in, and put a brand new cover plate on, and hopefully bring STS back to life. That's the good news. The bad news is that first cover plate has 115 screws on it, and there's a couple of other screws for a total of 117 screws. Tiny screws that are non-captive. They would just float around if you pulled them out in space. Non-captive screws that we have to remove in order to get access to these circuit boards. This is the kind of repair we've never done before in space. And we have to do it not only for the Space Telescope Imaging Spectrograph, STS, but we also have to do it to bring the Advanced Camera for Surveys back to life, ACS.
Well, the job of making repairs to the Advanced Camera for Surveys is actually spread out over a couple of EVAs. Tell us first what it is about this that you're going to fix, and what will that let ACS do in the future to contribute to Hubble's mission?
There have been two failures of scientific instruments on the Hubble Space Telescope that we're going to repair on this mission. The first one is the STS. The second is Advanced Camera for Surveys. Now, what's failed on the Advanced Camera for Surveys? The same thing that failed on STS. We have two power supplies. The first one failed. We switched over to the second. Everything was great. Then January of last year, the second power supply failed, and now ACS is down for the count. Now, fortunately, there's three cameras within Advanced Camera for Surveys. There's a wide field camera, a high resolution camera, and a solar blind camera. The solar blind camera was unaffected, but all these fantastic pictures we've gotten have come from the wide field camera within the Advanced Camera for Surveys. And that's dead right now, as is the high resolution camera. In order to fix that, the power supplies, the way we are on STS, we'd have to take Advanced Camera for Surveys out. And we can't do that. We don't have the time, and it's being blocked by the NICMOS fix that we did on the last mission. So always the clever folks, the Goddard engineers, have come up with a plan. Instead of trying to fix the power supply, we're going to mount a new power supply on the outside of the Advanced Camera for Surveys, and then pull out all of the electronics boards for the detectors and put new boards in. So instead of pulling one board out, we're going to have to pull four boards out. So maybe that's the bad news, that we have to pull out more circuit boards. And again, that's working in a vacuum in these gloves to work on boards that have sharp edges that we're not allowed to touch. The bright side is that we only have 32 tiny fasteners to remove instead of 117. On the Advanced Camera for Surveys, however, the access is not right in the front of the telescope of the instrument. It's off on the side. So my job will be to try and work around a corner, removing these 32 screws that, oh, by the way, I can't see when I remove them, and then pull 4 circuit boards out around a corner and put in a new box. Because this is a little bit more complex than the STS repair, we've split it over 2 days just to handle the contingency that it takes longer than we think. We're going to try and do it in 1 day. Might be a long day, but if it doesn't work, we have a breakout point that says, okay, if we've only removed 2 boards and it's this late in the EVA, we're going to close up shop and we'll come back on EVA 5. These repairs, ACS and STS, go well beyond anything we've ever tried in space before.
Well, there are things that were never planned to be done in space when it was designed.
For some reason, on all of my missions to the Hubble, the first 2 and then on this one, I'm a magnet for tasks which have never been done before in space. And I think that's just because I like the challenge and I seem to be good with doing those kind of repairs.
Now, of course, NASA wouldn't be NASA if you weren't going with plans to do things that aren't really in the timeline. Talk about the other repair and maintenance tasks that you guys have on Hubble.
Well, one of the tasks that doesn't appear as explicitly in our timeline as the major tasks is called the soft capture mechanism. And it's not really a task that we don't plan to do. We do plan to do it, but it fits in parallel with other tasks. And the soft capture mechanism is basically a set of petals that were like petals of a flower that we're going to put on the bottom of the Hubble Space Telescope, that someday, 2020 perhaps, maybe even later, we can send up a robotic spacecraft to grab onto the bottom of Hubble and deorbit it safely. Hubble is large enough and has this huge heavy mirror that some parts of Hubble will make it down to the ground, and we don't want it to fall on a city or on any place that could do damage. So it has to have a controlled entry and it has to be a guided entry, so it goes somewhere, say, into the Pacific. This soft capture mechanism will allow another spacecraft to come up and dock with it, and may be similar to the kind of docking mechanism that we're using in the Constellation program. That's one of the items that we'll do in parallel with the other tasks. We also have 3 new outer blanket layers, one of which we're certainly going to do on day 4 at the end of the STS task, but we have 2 other of these big pizza sheets that we're going to put on the outside of the telescope where the insulation has become damaged and is peeling up, and the stuff inside is either getting too hot or too cold. So we're going to fix those items. We also have a rendezvous and navigation sensor. This is pretty much independent of our spacewalks, but it's going to watch Hubble as it comes in and as we deploy it. And it will give us data so that eventually that robotic servicing mission to deorbit Hubble will have better access to coming up on the bottom of Hubble.
After the 5 spacewalks, it comes time to put Hubble back to work. Describe the plan for the reboost and then for releasing the telescope and leaving it in a stable condition.
Hubble's orbit decays, albeit very slowly, and the uncertainty in how fast Hubble will come down depends entirely on the behavior of the sun. We're entering a new solar cycle, and so we don't know how Hubble's orbit will change over time, but we know it will slowly come down. As a result, near the end of the spacewalks, the Mission Control Center will do an assessment of how much propellant we have left, and then we'll instruct Scott Altman and Greg Johnson, our commander and pilot, to slowly boost Hubble up to a new orbit. This is an example where the space station program has provided us a tool that we use on Hubble. Usually it's the reverse. Hubble tools are used on every single spacewalk on the space station. Well, now we're able to use something that we learned from space station, which is reboost with the shuttle to reboost the Hubble. And it's going to be done with just a series of very short bursts of our jets to slowly lift Hubble's orbit, perhaps as much as 10 miles. This could give it another 5 years of lifetime.
After the reboost, how do you send it on its way?
Once the reboost is complete and we've deployed the high-gain antennas from Hubble, open the aperture door. You can't see any stars if the end of the telescope isn't open. Take the lens cap off. We'll then grab Hubble with the robotic arm once again, open the latches that were holding it into the space shuttle, lift it up, and then in a kind of ballet, we'll release the snares that hold Hubble, back the arm away, and then Scott Altman will gently maneuver the shuttle back below Hubble and away, and Hubble will be starting what will be an entirely new journey.
And at the time, you guys will be the last people to lay eyes on Hubble as it floats away. Got any plans for that moment?
I like spontaneity, and certainly it's going to be for me, a very touching moment. When I first went to Hubble, at the end of our 3 spacewalks, we deployed Hubble on Christmas Day. And I had very mixed feelings. I had been working for a number of years on the Hubble project, had gone and done 2 spacewalks on that mission, and felt like I'd just barely gotten to know the Hubble before we had to send it on its way. But it was a glorious Christmas present to everybody on planet Earth, and it was a wonderful sight to watch it slowly drifting off on the Earth's horizon. I was privileged to go back again, and I felt like I was visiting an old friend. And I was convinced at the end of the last mission, as it floated away, that I would never get a chance to see the Hubble again, but I knew somebody would. And of course, that got thrown into disarray with the cancellation of the servicing mission on the shuttle. And so here I am going back to visit an old friend, to give it a new life, along with a team of some Hubble repeats, other Hubble huggers, and a new team. So I'm looking forward to that moment with some mixed emotions. But when we've successfully serviced the Hubble with all of the things we have on our plate, a very challenging mission and a very complex mission, when Hubble flies away, I'm going to be very proud of the shuttle team that allowed us to go there, and of the Hubble team that has come up with all of these fixes that will make Hubble just an incredible discovery machine.
When will the Hubble ground control teams have it ready to go back to work full-time and full strength?
After a servicing mission, there's a servicing mission period where they're just doing checkout. And the first part of that checkout is really just to let Hubble sit and let all the stuff that we brought with us dissipate. They have various sensors in the telescope that can tell what some of the contamination is, and also modeling that says after we've been inside of the telescope, they want to give it a good amount of time for all of the individual molecules to bounce their way out that came off of our spacesuits, that came off of the space shuttle, came off of the new things we installed on planet Earth, all the outgassing to occur, before they even turn the high voltage on the detectors. So it'll be probably a month or so before they really know how our repairs went. Then they'll slowly, part by piece, part by part, bring up the detectors, bring up the instruments, and then take some first images, some early release images. And I expect those to appear in about 2 months after our mission.
This mission seems to be a good example of the requirement into the future for people and robots to work closely together. How do you see this flight contributing to that future exploration?
I think Hubble is the best example of the marriage between human spaceflight and robotics. All of our robotic spacecraft have depended integrally on humans to operate them, whether it's the Hubble Space Telescope, which is operated remotely from planet Earth. Every detail of its existence is controlled and planned by people, and of course all the discoveries are made by scientists, not by Hubble. The rovers on the surface of Mars, every wheel turn, every point from here to 2 feet in front of the rover was controlled by somebody in the control room in Pasadena, giving an instruction and then watching the result. I think that linking between robotic spacecraft and people will be there for a very long time. Robotics is a very hard discipline, and you can't just set a robot down on planet Mars and say, go discover things. We're just not there yet. So I see that partnership extending to our lunar exploration, where we'll have people on the moon, we'll have robotic instruments and robotic rovers perhaps on the moon, and they'll be working in concert. And if a robot breaks, it's going to need a human or another robot instructed by a human to go and fix it. And I think that partnership makes our exploration much stronger. It leverages it exponentially over what each could do individually.